Good morning. Now this is the last class on our module oscillations. In this session we will learn about resonance and resonant frequency. See the graph here. That is, as we increase the value of P means the driving frequency or the frequency of the external applied force. What happens? The amplitude of oscillation, it increases, reaches a maximum value, and again if we continue to increase the value of P, what happens to the amplitude? It will start decreasing. So but at a particular value of driving frequency, amplitude of oscillation becomes maximum, this point. So that value of driving frequency at which amplitude of oscillation becomes maximum is called resonant frequency, and the phenomenon is called resonance. Okay, see the definition is written here. The phenomenon where for a particular driving frequency the amplitude of forced harmonic oscillator become maximum is called resonance, and the frequency at which resonance occurs is called resonant frequency. Now in order to obtain an expression for resonance frequency, we have to consider the amplitude of driven oscillator, which we have already derived in the last class. Now for this amplitude of oscillation to become maximum, the condition is that derivative of the square root of denominator should be 0, this one. Now you just differentiate this one with respect to P, you will get like this. Then finally you will get the value of P or the driving frequency or the resonant frequency PR as root of omega 0 square minus 2c square. Okay, so that means amplitude of driven oscillator is maximum when angular frequency is root of omega 0 square minus 2c square. Now this value of PR is less than the natural frequency of omega 0 and also less than the natural damped frequency omega of the oscillator. Now, in order to find the amplitude of driven oscillator at the resonance, what you have to do? You have to make a substitution in the above expression for amplitude. What was your expression? This one. Okay. In this expression, what you have to do is, you have to just replace or substitute the value of P that we have got, that is omega 0 square minus 2c square. Once you substitute the value of P as this in this equation, then the expression for the amplitude of oscillation at resonance will reduce to this one. Okay, now just open the bracket and simplify, you will reach at this equation, and we have already said that P is equal to root of omega 0 square minus 2c square. Here it is only 1c square, so in order to make it minus 2c square, you have to add 1 minus c square. So when you are adding that, you have to do like this also. Okay, that is, in place of this you have to make f0 by, that is, this will be again equal to f0 by 2c root of omega 0 square minus c square. Just put minus c square also. Since you put like that, you have to add 1 c square. This is of the form f0 by 2c root of, what is omega 0 square minus 2c square? It is PR square, right? Then plus c square is kept as this. That is how you got this equation. Now let's have some discussion on the results obtained. Okay, now equation 47, it tells you that amplitude of forced oscillator depends on the difference, that is omega 0 square minus p square. That means smaller the difference between omega 0 and p, larger will be the amplitude. Now what happens at very low driving frequency? Very low driving frequency means p very much small compared to omega 0. In that case, your amplitude A will be f0 by omega 0 square. Okay, or we can rewrite it as f0 by k. That means amplitude does not depend on mass of oscillating system or damping, but depends only on the force constant k. Okay, so that is one condition, or one condition where low driving frequency is discussed. Now second condition, when p equal to omega 0, your amplitude will be A equal to f0 by 2cp or f0 by 2c omega 0. Okay, This is, of course, from the expression it is very clear that it is less than the amplitude at resonance given by equation 52. So but in the case of low damping, amplitude becomes maximum at p equal to omega 0. That is quite natural. That is, damping means a source of dissipative force. So when damping is low, naturally amplitude of oscillation will also be maximum. Now the last one is at high frequency, that is when p is very much large compared to omega 0, your expression for amplitude is f0 by p square. That means amplitude will now depend on mass. Okay, and it will decrease continuously as the driving frequency P is increased. So these are the three conditions: at low driving frequency, at driving frequency, and at very high driving frequency. Okay, that is P less than omega 0, P equal to omega 0, P greater than omega 0. Under these three conditions, how the amplitude of oscillation look like. Last session is the sharpness of resonance. Now here equation 52, as already discussed, it suggests that amplitude of oscillator at resonance depend on the damping term. Okay, C is the damping constant. Now smaller the damping, naturally larger will be the amplitude of oscillation, or amplitude of oscillation will be maximum. Now from equation 51, we can see that in the case of small damping, that means when the damping constant C is very small, then your driving frequency or resonant frequency PR will be equal to omega 0. That means the oscillator will vibrate at natural frequency. When does that happen? At low damping. Okay, under this condition, amplitude of resonance is given by f0 by 2c omega 0. Okay, in an ideal case means when there is no damping, it is damping constant C equal to 0, the maximum amplitude becomes infinity. That is, when you put C equal to 0 in this equation, what will be A? It will be infinity. That is what it is written here. So we can conclude that damping controls amplitude response. Right? So when damping is low, amplitude of oscillation is high. When damping is high, amplitude of oscillation will be low. Okay, so damping controls amplitude response, and this response is shown in this figure. That is, the figure shows the variation of amplitude with driving frequency for different amounts of damping. So you just understand this. That is, when damping is low, amplitude of oscillation is maximum. When damping is high, amplitude of oscillation will decrease. It will be low. That is, damping controls the amplitude response. And here you can see the various response of amplitude for no damping, small damping, large damping, very large damping, etc. Let us analyze this figure. Now the figure shows that as driving frequency deviates either way from its value for the resonance, amplitude falls from its maximum value. See, amplitude is falling from its maximum value. If the amplitude falls rapidly with the change of driving frequency, we say that resonance is sharp. So here the resonance is sharp because as we increase the value of driving frequency P, this amplitude of oscillation decreases rapidly or sharply, and we say that the resonance is sharp. That is, resonance is sharp in the case of no damping case. The smaller the damping, the sharper the resonance, which is very clear from this graph, right? Note that for large damping, resonant frequency is less than omega 0. In that case, how will be the fall look like? That is, the fall in amplitude. It will be small and resonance is said to be flat. See, here the resonance is almost flat for large damping, right? That is, amplitude of oscillation is not decreasing rapidly. But in the case of small damping, amplitude of oscillation decreases very sharply. That means we say that resonance is sharp. Okay. For higher values of damping, resonance peak shifts more and more towards the left as shown. Now, what is meant by sharpness of resonance? One definition: the rate of fall of amplitude from its maximum value at resonance on either side of resonant frequency with the change of driving frequency. Okay, that is called sharpness of resonance. We can observe a sharp resonance in the case of sonometer wire where damping is very small. In the case of resonance column where the oscillations are subjected to a large damping, resonance will be flat. So here you will get two examples for sharp resonance and flat resonance. So this paragraph is important. Okay. So resonance is an important session. Just go through it, okay, especially the sharpness of resonance. Okay, thank you.